Hi, this is Presh Talwalkar. In this video, we're going to count to infinity and beyond, and we're going to learn about a special class of numbers called transfinite ordinals, which can arise in infinite chess. But to get started, we're going to consider a puzzle from a regular game of chess. Here's a position on the board, and it's white's turn to move, and white needs to be able to checkmate black in 2 moves. This is a typical type of chess puzzle, and the way you work it out is you consider all the ways that white could move and all the ways that black could counter-respond in the best possible way. When the puzzle says that white can mate in 2, that means there's a strategy that white can force black to make moves, and white can still win within 2 moves. So in this position, it looks like white is at a great disadvantage because black has a couple of pawns and everything is protected. However, white can utilize its knight to force black into a bad position. If the knight goes to e6, it checks the black king, and there are only 2 positions the king can go. It can either go to the corner or it can try and evade one more to h7. But no matter what the king does, white's rook can respond by going to that column, and it's a checkmate. The king has nowhere to go. The knight is blocking the 2 exits, and the entire column is blocked by the rook. So this is an example of a chess puzzle and how white can win in 2 moves. So now let's do a more complicated puzzle. This is a puzzle where white has a turn to move and can mate in 5 moves. Here white looks to be at a great disadvantage. Its king is out in the open, it only has a knight and a queen, whereas black has 2 rooks, a queen, and a somewhat defended king and 2 pawns. So how is white going to be able to force a mate in exactly 5 moves? White can get started by putting a check on the king. Now the king could make a stupid move by moving to f8. But if the king moved over there, then white would obviously have a checkmate right here at f7. So in these types of puzzles, we're going to assume that black and white are making the best possible moves. So we want to avoid these kinds of stupid moves where it would result in an early checkmate for black. So we're going to assume black is not going to make that bad decision of going to f8, and instead black is going to go to the corner and evade the checkmate. White's knight can respond by putting a check on f7. At this position, black only has one way to go. It needs to move the king, and it needs to move it back to g8. Now white can move its knight and reveal a check and also give a double check. So this puts the black king once again in a bind, and the only way to get out of it is to move back to the corner. And now comes the brilliant move in this sequence. White is going to sacrifice its queen and smother the king. In this position, the king can't take the queen because it's being protected by the knight. So the only way that black can get out of this is by killing the queen with its rook. And that is the trap that white has set up, because now the knight can go to f7, and that's a checkmate. So this is known as a Smother Checkmate, and this is an example of how white can finish off the checkmate in 5 moves. So we're going to take this puzzle and mathematically define a few concepts. So in this final position where white has checkmated black, we're going to define this as a position of the board that has value 0. White has already won the game, and so it has a value of 0. We are then going to define that a position on the board has value alpha plus 1 if white can move to a position that has value alpha. So right now we have a value of 0, so if we go back 1 move, that would be a position on the board which has value 1. Because from here, white can move to a checkmate, which is a value of 0. If we go back one more move of black and white, this is a position where white can force a checkmate in exactly 2 moves. So we would say this position of the board has a value of 2. And we could go back in that same puzzle to all the way to a value of 5. But basically, intuitively, a position of the board has value alpha if white can force a checkmate in exactly alpha moves. One thing I'll say is that we don't know what the value of the starting position of the game of chess is. We don't know if it's a guaranteed win for white, or if it's going to be a draw or a guaranteed win for black. So some positions, we may not have actually calculated it because there's so many chess positions that are possible. But in puzzles where we know white can guarantee a mate or black can guarantee a mate, we can determine what the value of those positions are. So we've demonstrated chessboard positions which have finite values going up to 5, and of course you can demonstrate them for higher values. But there are actually some interesting values that you can get on the chessboard in a special game of chess. So before I get to that, I want to talk about the transfinite ordinals. So let's imagine counting to infinity and beyond. So the counting numbers have a very specific order. We know that 1 comes after 0, 2 comes after 1, 3 comes after 2, and so on. So every single number in the counting numbers has a specific ordering, and we know that something comes after it. So in set theory, you can actually define something very interesting, which is you can define something which comes after all of this. So this would be a limit ordinal called omega, and this is the first transfinite ordinal. So it's a very specific and kind of complicated way to define it. I'm going to gloss over the details for this. But basically, you can have a number which comes after all the counting numbers. From there, you can actually say, all right, let's add 1 to that number, and we have omega plus 1. We can apply the successor relationship, which is well defined in this operation, and you can count to omega plus 2. You can continue counting all the way up to omega plus omega, which will end up being the number omega times 2. And we might as well just keep going. We can go to omega times 2 plus 1, and if we keep adding, we'll eventually end up at omega times omega, which we'll denote as omega squared. And naturally, if we keep on counting, we'll end up to a point where we're multiplying omega times itself, omega times, which will be omega to the power of omega. So we've counted some really huge numbers here, but just keep in mind, these are actually all very special kinds of sets. So they're what's known as countably infinite sets, and they're all well-ordered sets. And there's some very interesting theorems that we call these the ordinals, because these are every other type of way we can have well-ordered sets will actually be isomorphic to one of these. And if you keep on counting, you can actually get to the uncountable transfinite ordinals, which is a whole separate topic. But for now, let's just deal with some of these countably infinite or transfinite ordinals. So, what's the point of all of this? Well, these kinds of numbers actually come up in combinatorial game theory. And using a special game of chess and some of the puzzles we've gone through, we're going to demonstrate a game which has an interesting value of omega. So let's consider this puzzle, and I've provided a reference for the paper where this comes from. So this is kind of a special game of chess. You know, this isn't a real board. White doesn't have a king on it. And, you know, black has 3 rooks. But still, the point of the game is that black wants to avoid being checkmated, and white wants to checkmate black. So we can analyze this game that suppose black is to play here, and black wants to avoid being checkmated, white wants to get to a checkmate. What is the best possible way that both players can play? So this is like a chess puzzle that we've been solving, but it's a different configuration. There's no white king, so obviously there's no way that black can create a checkmate. So the only thing black can try and do is avoid the checkmate, and white is going to try and checkmate. So if you go and analyze this position, there are a lot of different ways you can go through, but there's actually only one thing that can happen here. Black can try and avoid a checkmate by moving the rook up, and white is actually going to have a mating net where it moves with the rook and the queen. This is a very famous mating pattern. And so the black king moves out of the way, and once the white queen moves up, there's nowhere that the black king can go. This is checkmate. So we could say the starting value of this fictitious board would have had a value of 2, because white was able to checkmate black in 2 moves. So now let's continue this example. Let's imagine we started everything just 1 position down. So once again, there's really nothing else for black to do except move its rook 2 positions up. So now this creates 1 extra spot where black's king can evade. So when white applies the same mating net procedure, it's going to result in a checkmate, but it's going to result in a checkmate in 1 more move than before. So the starting value, the position of this board actually had a value of 3. So now we can generalize this. Let's imagine we're playing the same game, but instead of just being limited to the regular chessboard, let's imagine it's an infinite board, so it goes infinitely high up. So instead of stopping at 8, it continues infinitely high up, and it continues infinitely high on both sides. So the rook could actually move infinitely high up. This will create an infinite number of spaces where the black king can evade the mating net procedure. So eventually we know that white is going to win this game. It's a guaranteed win for white, and white is going to do the same mating procedure. But there's no trap right here. So this black king can actually just continue to move up. Eventually black is going to lose this, but what's the value of this game? We know it's a win for white, but it has to be bigger than every counting number that we know. So the answer is this game has a starting value of omega, because this is going to be the first number that's larger than all of the counting numbers. So we've demonstrated a game which actually has a value of a transfinite ordinal. So these transfinite ordinals, we think they're just interesting concepts, but actually we can demonstrate in combinatorial game theory they have an application that this infinite game of chess has a value of omega. There are other complicated games I've provided. You should check out this paper if you're interested in learning more about it. There's a lot of interesting details. They've actually come up with some games which have values like omega squared and omega to the 4th. So it's really neat that these transfinite ordinals have found a use that they can arise in the game of infinite chess. So I hope you appreciate that you've learned a different set of numbers, and you've also learned about the game of infinite chess. Thanks for watching this video. Please subscribe to my channel. I make videos on math and game theory. You can catch me on my blog, Mind Your Decisions, which you can follow on Facebook, Google+, and Patreon. You can catch me on social media @PreshTalwalker. And if you like this video, please check out my books. I provided links in the video description.